solve the following system algebraically and graphically. And we are given a system of linear equations with two variables, 3x plus 4y equals 1, and 5x minus 2y equals minus 3. And so we want to start here by solving this system algebraically. Again, knowing our solution point, our intersection point, when we go into sketching the graph, especially without a calculator, makes our lives a lot easier. So we'll start by labeling our equations. I have equation 1 and equation 2. And then looking at the variables here and looking at their coefficients, I notice that the y variables have opposing sides. So I'm going to use the process of elimination here. I'm going to go ahead and multiply equation 2 by 2, and then add it to equation 1 to eliminate y. So do a little scratch work out here first. And we'll keep in mind that when I'm multiplying equation 2 by 2, so if I have 2 times 5x minus 2y is equal to negative 3, or negative 33, I want to be mindful that I distribute this 2 through to each piece of the equation here on both sides. So again, we're going to do 2 times equation 2, and we're going to add it to equation 1 to eliminate the y variables. So 2 times equation 2 gives us 10x minus 4y is equal to minus 66. And now I'm adding equation 1, which is still 3x plus 4y is equal to 1. And then we see here the minus 4y plus 4y goes to 0. And we have now 13x is equal to minus 65. And so to isolate x, we'll divide both sides of this expression by 13. So 13 by 13 goes to 1. And we have that x is equal to negative 5. So we have the x-coordinate of our solution point, and we'll now go ahead and we can substitute x equals minus 5 into either equation. And that's to find the corresponding y value. So I encourage you, a great way to check your work, if you have time, is to plug x into both equations, and you should get the same answer no matter what. So here I'm going to use equation 1 as it's given in the question. So this will become 3 multiplied by negative 5 plus 4y is equal to 1. And we're ready to start solving for y. So I have minus 15 plus 4y is equal to 1. And we can go ahead now, we'll add 15 to both sides of the equation. So minus 15 plus 15 goes to 0. We have 4y is equal to 16. And now, last but not least, to isolate y, we're going to divide both sides of the equation by 4. So 4 divided by 4 goes to 1. We are left now with y is 4. So we now know that the solution point, or the coordinates of our intersection point of these two lines, is defined as xy is equal to negative 5, 4. So this is our answer for the algebraic solution. And now we want to go ahead and solve this system graphically. And so to do that, we want to convert each of our given lines to their slope-intercept form. And so we'll keep in mind that our slope-intercept form is defined as y is equal to m times x plus b, where b is our y-intercept. So by converting each line to its slope-intercept form, we have another ordered pair that sits on the line. And we know that we only need 2 points to sketch the graph of a line. And we already have 1. So by solving here, we find the second. So equation 1 is given to us as 3x plus 4y is equal to 1, and we want to solve for y. So we'll start here by subtracting 3x from both sides of our equation. 3x minus 3x goes to 0, and we are left with 4 times y is equal to minus 3x plus 1. And then to isolate y here, we can divide both sides of this equation by 4. So this leaves us with the slope-intercept form, y is equal to minus 3/4 times x plus 1/4. And so we can see that our y-intercept is the ordered pair 0, 1/4. And now we want to go ahead and do the same thing with equation 2, which is given to us as 5x minus 2y is equal to minus 33. And again, we want to solve for y. So to keep everything positive, I'm going to switch the positions of minus 2y and minus 33. So this is going to leave us with 5x plus 33 is equal to 2y. And then to isolate y here, we can divide both sides of the expression by 2. So 2 divided by 2 goes to 1. And this leaves us with y is equal to 5 halves times x plus 33 halves. And so we have a y-intercept here at 0, 33 halves. And before we start sketching this graphically, we'll just make a little love note here to ourselves because we're working with fractions. That 1/4 is equal to 0.25, so it's going to be closer to 0 than 1. And then we have 33 halves. So if we convert this to a mixed number, we know 2 goes into 33 16 times with 1 left over. So we have 16.5. So we want to always plot with the exact ordered pairs that we found, but thinking about decimal approximations or mixed numbers can be helpful in establishing our scale. So since we have such a large y value for one of our intercepts, we need plenty of room. So let's say here is our y-axis, and here's our x-axis. So establishing our scales, we have 1, 2, 3, 4, 5. So that's -5 on the x-axis, and then 1, 2, 3, 4. And then so for y, we have 1/4 and then 16.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So up there is 17. So it may have been easier in a case like this to use a smaller scale than a 1x1, or excuse me, a bigger scale. All right, so we'll start here by plotting our intersection point, which occurs at -5, 4. So we have an ordered pair right about here. And this point, again, is the solution point, or the point that sits on the graph of both lines. Thinking about equation 1, we know we have a y-intercept at 0, 1/4. So way down here is the y-intercept, and then if we connect our intersection point to this y-intercept, we have a graph of equation 1, which we converted to its slope-intercept form, y is equal to minus 3/4 x plus 1/4. And now doing the same thing with our second equation, equation 2, we're making a note that it has a y-intercept at 33 halves, or 16.5. So right about there. So that is the ordered pair 0, 33 halves. And again, connecting our solution point to this y-intercept. We now have a nice graph of equation 2, which we converted again to slope-intercept form. Y is equal to 5/2 x plus 33/2. And then shame on me, I did not label our first y-intercept down here, which is at 0, 1/4. And so this is solving our system of equations graphically.